Hello friends, welcome to engineering tutorial. Now in my previous 2 or 3 videos I started the concept of biased clipping circuits. Previously we discussed about positive and negative clipping circuits, and then we started discussing about biased clipper circuits. In my first video related to biased clippers, I gave a basic introductory concept to the bias clipper circuits, where we discussed about the basic definition of bias clippers and the various types of output that we can get for a particular input signal depending upon the various types of bias clipping configurations that we are using. So in my just previous video, we discussed a particular circuit configuration of bias clipping circuit. Now from the output waveform which we studied, we found out that it was a positive biased clipper. It means that only certain portions of the positive half cycle were removed or clipped. Now today we are going to discuss another circuit configuration of bias clipper circuit, and from the output waveform we will get to know what type of bias clipper circuit it is, whether it is a positive bias clipper circuit or a negative bias clipper circuit. So before you go into this video, I would request you to please check out the just previous video related to bias clipper circuits, so that you completely see that video, so that you understand this video in a better way. So let us start. So this is the circuit diagram of today's circuit configuration of bias clipper circuit. So you see the components are the same which were there in the previous bias clipping circuit. As usual, the input signal, again we have taken a sinusoidal input. The resistance are the diode D, which is connected along with a reference voltage or biasing voltage, which is a DC voltage, and then the load resistance RL across which the output is obtained. This resistance R, as I have already told, protects the diode from excessive voltage or current surge. Now, how is this circuit different from the one which we just previously discussed in the previous video? Pay attention to this diode. Okay, it is connected with its N end upward and the P end downward. N end up and P end down. But in the previous video, the circuit configuration of bias clipper circuit which we discussed, the diode was in inverted position. Okay, just rotated by 180 degrees. It means that the P end was towards the top while the N end was to the bottom. The P end is this arrowhead type and the N end is the bar type. So you can see its inversion, the position of the diode is inverted. Okay, the reference voltage is the same, but only the direction of the diode is changed. The direction of connection of the diode is changed. So in this circuit it is connected in this fashion. In the previous video related to bias clipper circuit, the configuration 1 which we discussed, the diode was connected in this fashion. Okay, so let us see how this change in the position of the diode connection affects the output waveform. So again, this reference voltage or biasing voltage plays a crucial role. If we remove this biasing voltage, it will be a normal clipping circuit, which can either be a positive or negative clipping circuit depending on the type of waveform which we get. But if we add this biasing or reference voltage, it will become a biased clipper circuit. If we remove this, it will be a normal positive or negative clipping circuit. If we add this reference voltage, it will become a biased clipper circuit. That's why it is called as a biasing voltage at the reference voltage. This voltage decides above or below which voltage level clipping will take place in the input signal waveform. Okay, so just similar to the circuit configuration 1, okay, of the bias clipper circuit. This circuit will be studied or analyzed in two cases, in two conditions. In case 1, the input voltage is lesser than the reference voltage. So, we will study the output voltage behavior when the input voltage is lesser than the biasing or the reference voltage. So, we will see how the output changes with respect to change in the input signal voltage. In the second case, we will analyze the circuit when the input voltage is more than the reference or biasing voltage, that is, the input voltage is greater than the reference or biasing voltage. We just did the exact same thing in circuit configuration 1 while discussing circuit configuration 1. So, because of this presence of the reference voltage, we have to analyze the circuit in two cases so that we can understand the output behavior in a simple way. Okay, so we will analyze this circuit in two conditions, when Vi is lesser than Vr and when Vi is greater than Vr. Okay, so let us see how the output behavior, the output signal behavior changes with respect to the input signal voltage in these two cases. So, we will study the circuit, the bias clipper circuit configuration 2, in this case, case 1, where the input voltage is lesser than the reference voltage at the biasing voltage. Here the input voltage is a sinusoidal signal and the reference voltage is a DC voltage, constant. So, we will analyze the circuit when the input voltage is lesser than the reference voltage. Again here, the behavior of this diode becomes crucial. Okay, here again the concept of forward and reverse biasing of the diode will come into play and will determine the behavior of the circuit and the output voltage level. So, please pay attention to this diode which is connected here in this circuit. You can see this arrowhead or the p-type end is connected to Vr, the biasing or the reference voltage. It is a DC voltage. The p-type end is connected to Vr. The n-type end is connected to the input voltage, the sinusoidal signal. It has been given that the input voltage is lesser than the reference voltage. So, we can say that the p-type end is connected to a higher potential and the n-type end is connected to a lower potential. Vi is lesser than Vr, Vi is connected to N, Vr is connected to P. So, the p-type end is connected to a higher voltage and the n-type end is connected to a lower voltage. So, we know that when a diode is connected in this fashion, it will be forward biased, and when a diode is forward biased, it behaves as a short circuit. So, I have posted 2 or 3 videos related to forward and reverse biasing of PN junction diodes. So, you please check out those videos in my channel so that you understand this forward and reverse biasing of diodes in a better way. So, in clippers, this forward and reverse biasing of diodes is very crucial and important, and it determines the output of the circuit, the behavior of the circuit. So, here the p-type end is connected to Vr, the n-type end is connected to Vi. As Vi is lesser than Vr, it means that the p-type end is connected to a higher electric potential and the n-type end is connected to a lower potential. So, in this case, the diode will behave as forward biased and it will be short circuited. So, the entire reference voltage, the DC voltage, will appear across the load resistance as output, and the output in this case, case 1, Vi less than Vr, will be a constant value which is equal to the reference voltage or the biasing voltage. So, when the input voltage is lesser than the reference voltage in this type of circuit configuration, the output will be equal to the reference or biasing voltage used in the clipper. So, the output is equal to the reference or biasing voltage in this case, Vi lesser than Vr. Now let us analyze case 2 where Vi is greater than the reference or biasing voltage. So this is the second case in which the input voltage is greater than the reference voltage. So as you can see, this input voltage is greater than the reference or biasing voltage which is connected here. So now again pay attention to this diode connection. The N end is connected to the input voltage, the P end is connected to the reference or biasing voltage. It has been given that the input voltage is greater than the reference voltage. It means that the N end of the diode is connected to a higher potential and the P end is connected to a lower potential. Okay, Vi is greater than Vr, so the N end is connected to Vi, the P end is connected to Vr. It means that the N end is connected to a higher potential, the P end is connected to a lower potential. So the diode in this type of connection, it is reverse biased. Okay, it is reverse biased, and when a diode is reverse biased, it will behave as an open circuit. Okay, again the N end of the diode, this bar end, is connected to Vi, the P end is connected to Vr. Vi is greater than Vr in case 2. It means the P end is connected to a lower potential and the N end is connected to a higher potential. So the diode will be reverse biased and will behave as an open circuit. Now, because of this open circuit, this reference voltage, it goes out of the equation, it goes out of the circuit, it becomes it is not involved any longer. Now R and RL, this resistance R and the load resistance, they are now in series because of the open circuit with the input voltage. So we can apply voltage division rule to calculate the output voltage across the load resistance. Now this is the same thing which we did in the previous clipper circuit configuration 1. So R and RL are now in series. So applying voltage division rule, we get the output voltage V0 as Vi into RL plus by R plus RL. We have simply applied the voltage division rule, okay, to calculate the output voltage across RL. Now this resistance value R is generally much lesser than the RL, okay, the RL value. The RL is much greater than R. So in the denominator, this term, it can be easily replaced with RL because this R value is much lesser than RL. So this sum will be nearly equal to the load resistance value R. So when we replace this in the denominator, we get the output voltage is equal to Vi into RL by RL. RL will be cancelled from both the numerator and the denominator, and the output will be nearly equal to the input voltage. So it's almost equal to the input voltage. So we get exactly the same input signal waveform as the output in case 2 where the input voltage is greater than Vr. In case 1, the diode was forward biased. As a result of forward bias, it was short circuit, and because of short circuit, the output voltage was equal to this reference voltage. So it was a constant value, okay, in the first case where Vi was lesser than Vr. In this case, case 2, when Vi is greater than Vr, the diode is reverse biased. Because of that, it is open circuited, and as it is open circuited, these two resistances, they are now in series. So voltage division rule comes into play, and we apply that rule to calculate the output voltage across the load resistance, which we calculated as nearly equal to the input signal voltage. So we will get exactly the same shape as that of the input signal waveform as output in this case when the input voltage exceeds the reference voltage value. Okay. So now let us see the relationship between the input and output signal waveforms. Okay. So now we will study the relationship between the input and output signal waveforms of the bias clipper circuit configuration 2, which we just discussed. So this is the input signal, which is a normal sinusoidal signal consisting of both the positive and the negative half cycles. Now in this input signal, the important thing to take notice of is this reference voltage. It is a constant value, okay, this DC voltage, the reference voltage or the biasing voltage. Now before we discuss the input and output signal waveforms, let us just have a look at the conclusions that we just derived or drawn from the circuit analysis in these two cases. In case 1, when Vi is lesser than Vr, when the input signal is lesser than the reference voltage, the output is equal to the reference voltage. In case 2, when the input voltage is greater than the reference voltage, the output is equal to the input. It means that the output follows the same signal waveform shape as that of the input signal waveform. Okay? So these are the two conclusions that we derived from this circuit analysis in two cases. Now, just look at this input signal waveform. From origin, from the start up to this point A, means the reference voltage Vr. This input signal is lesser than reference voltage. From OA, from O to A, input signal is lesser than reference voltage. Okay, it is below the reference voltage. This much portion of the input signal is below reference voltage. It means that the input signal is lesser than the reference voltage. So if we trace the output will be equal to the reference voltage in this case when Vi is lesser than Vr. So for the entire portion OA where input is lesser than Vr, if we trace the output, it will be a constant value Vr. It will be a constant. If we trace the output from O to A where Vi is lesser than the reference voltage, if we trace the output, it will be a constant value. V0 is equal to Vr. Okay. Now from A to B, from point A to point B, the input voltage lies above Vr, the reference voltage Vr. From A to B, input voltage is above Vr. It means the input voltage is greater than Vr. So in that case, the output is equal to the input. The output voltage is equal to the input signal voltage. What it means that the output, it will follow the same shape or the same signal waveform as that of the input signal waveform. So now this is a curve from A to B, the input signal, the portion of the signal from A to B is a curve. Here also it follows the same shape, the output follows the same shape. Okay, this output follows the same shape. From A to B, the output follows the same shape. Now from B downwards, the curve, the signal, it goes downwards. It means for the entire portion from B, it lies below the reference voltage Vr. Okay, this much portion, it lies below the reference voltage Vr. It means from B onwards, the input voltage will be again lesser than the reference voltage. Okay, the input voltage will be lesser than the reference voltage. So again, the output voltage will be a constant value. It will be a straight line parallel to the x-axis of the value or magnitude equal to the reference voltage. So again, it is equal to Vr, it is a straight line parallel to the x-axis or the omega t axis, again for the entire duration of the negative half cycle. So when up to from O to A, input voltage is lesser than the reference voltage, so V0 is equal to Vr. From B onwards, again input voltage is lesser than the reference voltage, so V0 is equal to Vr. Only for the duration of the signal from A to B, where input voltage is above the reference voltage, it is greater than the reference voltage, the output voltage is equal to Vi, so it follows the same shape, the same signal waveform as the input. So the output follows the input. So this is how the output waveform signal looks like. So here you can see these dotted portions and the entire negative half cycle is removed or clipped. Now, here only the changes that have happened are in the positive half cycle. Okay, I have already told you in the introductory video related to bias clippers that where bits and pieces changes are made to a particular half cycle, only that half cycle is considered to be clipped. Here our intention was not to remove the negative half cycle, it was a byproduct of this circuit, but only the changes have happened in the positive half cycle of the signal. The top portion of the positive half cycle is retained, the bottom portion below VR has been clipped or removed. So it is a positive bias clipper. The negative half cycle is removed because of the circuit connections, but here no bits and pieces changes have happened to the negative half cycle. It is entirely removed. So in any type of clipping circuit, a half cycle will either be entirely present or entirely absent. But where in the half cycle where bits and pieces changes happen, that is considered to be the clipped signal. So here bits and pieces changes have happened to the positive half cycle. Certain portions of the positive half cycle have been retained, certain portions have been removed. So it is a positive bias clipper because changes have happened only in the positive half cycle. The negative half cycle can either be completely present or completely absent. I think in the previous circuit, the circuit configuration 1, this half cycle was completely present, negative half cycle, but only changes were happening in the positive half cycle. Here also the changes are happening only in the positive half cycle. The top portion is retained, the bottom portions are removed. So it is a positive bias clipper. This circuit which we discussed, the circuit configuration 2, it is a positive biased clipper. Okay, it is a positive bias clipper because changes to the signal waveform have happened only in the positive half cycle. The negative half cycle is not touched. It can either be completely present or completely absent. In this case, it is completely removed. In the previous circuit, it was completely present. So the changes have happened only in the positive half cycle. Okay, bits and pieces changes. It means the positive half cycle top portion is present, the bottom portion is removed. So it is a positive biased clipper. So here we have discussed another circuit configuration of the bias clipper circuit, which again turned out to be a positive bias clipper. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics, instrumentation and communication engineering, and we'll try to keep posting more and more videos related to various concepts related to electrical and electronics engineering. Have a great day. Thank you very much.